op-amp. Yeah, simplest op-amp is a two-stage op-amp. So because simple differential pair, the voltage gain is not large enough usually. Or like we want a voltage gain of around 6 dB, 60 decibel, which is 1,000. Yeah, so sometimes, I mean, mostly that single differential pair, the voltage gain may be 100 or maybe 600, something like that. So I need a two-stage. Then my voltage gain is just a multiplication of those two, okay? Then I can achieve a voltage gain larger than 1,000. That's why we need a two-stage op-amp. Yeah, another alternative is folded cascode op-amp. This folded cascode op-amp, it increase the voltage gain is just input transistor GM times output resistance. Okay, this is a single stage. It increases RO, and then voltage gain. This is a single stage amplifier. Okay. Yeah. Let's just start with that differential pair. Yeah, this is my MOS input differential pair. Let's just see. I will change this thing into circuit like that. For example, this is NG1, okay? Then I have a second stage here, say, which is PMOS transistor and the NMOS transistor there. This one is connected to there. So this one is connected to there. So this is my output. So yeah, see, this is a VO1. Yeah, for the differential input, yeah, my VO1 is only GM1 RO1. This is RO1. GM1 RO1 times VID. Okay. Yeah, my VO is just minus GM5 times RO times VO1. Okay. This is my RO. This small signal output resistance is just RO5 parallel RO6, okay? Yeah, there are some parasitic capacitance here and there, right? There are some parasitic capacitance here too. Because of those parasitic capacitance, so signal becomes slowed down. Okay, when signal is applied here, this signal shows up here at the late. I mean, there is some delay time from here to there. Okay, that's called the phase shift. Phase shift. Yeah, but in the time axis here, this is my input. Then my output looks like that. See, output is delayed. Oh, sorry, it's a same frequency increased, but it's a delayed because of those capacitance. Okay, that phase shifts cause a problem if I apply this one into input by feedback. Yeah, let's look at the SPICE simulation of this one. Let's see. Oh, where is my two-stage op-amp? Oh, yeah, here. Overflow. Uh-oh. How come? Oh, yeah. Okay. Okay, let's look at the two-stage op-amp. Let's see. We use the same differential pair, 10 by 10 and the 1 by 10 for PMOS. But that cascade part is eliminated for simplicity. The cascade current source is just a single stage current mirror. Okay? And then added the second stage here. This is only PMOS is 1 by 1, NMOS is 10 by 0.7. Wow, how come? This is 20 by 0.7. Okay, let's draw the circuit. Let's draw it again here. This is NG1, okay, and then this is, I have a PMOS transistor there. Oops, where am I? Yeah, it's gone. Yeah, this is 1 by 10, this is 10 by 10, 20 by 0.7. So I increased the current. This is 100 by 27, 5 times. This is 10 by 10, 1 by 1, or something like that, 1 by 1. So at the steady state, we flow current here 200 nanoamp, right? So here we flow current 100 nanoamp. Then because I want a symmetry, then because this is 10 times, this current flow 1 microamp, right? How about here? Yeah, 5 times, yeah, 1 microamp, okay? It's okay then, right? So I have some, I don't have offset problem. Yeah, 100 nanoampere here too. Yeah, this must work in a strong inversion. So this also must work in the strong inversion, because gate source voltage are the same by symmetry. Okay, gate source voltage are the same. Then here's yeah, because their gate source voltage are the same. This should work sub threshold, right? Sub threshold. Or all they work in sub-threshold. Okay? So, yeah, this GM, let's see, how about this is a strong inversion GM, right? Let's see. How much larger is this GM compared to that one? This is a GM3, M3. What's this thing? This 4, 5. This is 5, 6, 7, something like that. Okay. How large is the GM5? Strong inversion, right? Gate source voltage. I think GM5 is 10 times larger than GM3. Because in strong inversion, GM is just mu Cox W over L VGS minus VTH, right? So they have the same gate source voltage. It depends on W over L ratio, okay? Okay, let's just simulate this thing. Where is my two-stage thing? Oh yeah, here. DC tran. Let's look at the tran. What do I have here? Input. This is my input. This is my output. That's a D1. So D2 and D5. I want to delete out D1. Okay, let's look at it. So my G1 is this yellow one changes from 0 to 3.3. My G2 changes from 3.3 to 0. And then my D2, which is first stage output, you know, this cyan color. So this is my D2. And my final output of a two-stage amplifier is that green thing. Green thing, it changes very sharply, right? Output voltage range is pretty large, almost full swing. That's the main advantage of a two-stage op-amp. Large output voltage range, okay? Very large output voltage range. So let's look at the frequency response. Yeah, that's a transient. Where is my AC? Did I do the AC analysis? Let's look at it. Where is my AC? Oh yeah, AC is AC 0.5. This AC minus 0.5. So it is a differential input. Okay, do I have that one here? Oh, two-stage AC. I don't have AC. How come? Let's look at the code again. Oh, AC is there. How come it doesn't print out AC? Oh, it should. Some problem here. AC D5. How come I don't have AC output? Two stage. I don't have AC output. Looks like some problem here. It has a very run simulation aborted. AC analysis. Yeah, we'll do it later after this folded cascade stuff. Okay? Question? Okay, question is why do we increase current at the second stage? Uh-oh. Yeah, so it increases GM2 than GM1. Yeah, it's good for frequency response. Okay, say, you know, dominant pole, the dominant pole means the lowest frequency pole. Gain bandwidth product equal, let's see, this is a GM1 CC or something, okay? Non-dominant pole, CC is a frequency compensation capacitor. So we want to increase non-dominant pole frequency much larger than this dominant pole frequency. I need a larger GM2 than GM1. Yeah, we'll talk about the frequency compensation later. Okay. Okay, with the frequency simulation.